This is an AP Chemistry, Unit 1, quick review of instrumentation. So this is by no means a comprehensive review, but we are going to highlight some of the instrumentation techniques and do some sample problems to remind you of material that we did way back in Unit 1. So in this review, we will be talking about spectroscopy, which is the interaction of matter and EMR, electromagnetic radiation. So we'll go over mass spectroscopy, PES, photoelectron spectroscopy, UV-Vis spectroscopy, IR, microwave, and we'll do a little bit of chromatography as well. All right, so we'll start out with mass spectroscopy. So when we have a mass spectrometer, we have a sample of an element, we put it in the instrument, and we get three pieces of information. So we get the number of isotopes of the element. The instrument gives us the percent abundance of each isotope. And the mass of one atom of each isotope. And from that information, we can calculate the average atomic mass. So our formula for doing the calculation is that our average atomic mass is equal to the sum I equals 1 to n, where n is the number of the isotopes, of the decimal percent, the percent expressed as a decimal, of I times the mass of one atom of I. And again, n equals the number of isotopes. So we'll do an example problem here, and I'm just making up these numbers. You can't go looking on your periodic table and find the element for this. All right, so we're going to say that our element X has two isotopes. So we'll say isotope 1 is 38.6% abundant and has a mass of 110.5 atomic mass units. Our second element has an atomic mass of 115.6 atomic mass units. All right, so I encourage you to pause the video and do the problem on your own, see how well you do, and then when you're finished, come back and check on your answer. All right, so we're going to solve the problem now. So our average atomic mass for element X is equal to the percent abundance of our first element, so that is 0.386 times 110.5 atomic mass units, plus, now we need the percent abundance of our second isotope. The problem didn't give us that, but our percent abundances must equal 100%. So based on that, then this has to have a percent abundance of 61.4%. They must add up to 100. So we have 0.614 times 115.6 atomic mass units. And we just do that math, and our unit is atomic mass units. So let's see what we get. 0.386 times 110.5 plus 0.614 times 115.6 equals All right, take that out of scientific notation, and we get 113.6 atomic mass units. So no one atom in the sample has that mass. Some have this mass, some have that, but the weighted average is 113.6. Okay, so now let's do another problem that is a little bit trickier. So for this problem, we're going to say that element Q has an average atomic mass of 79.30 atomic mass units. The masses of the two isotopes are 78.19 and 83.00 atomic mass units. What is the percent abundance of each isotope? Okay, so again, be a good idea to pause the video, see if you can solve that problem, and then come back and check your answer. Okay, so we have our formula. So this time we're given the average atomic mass, so we're going to start out with that. So we know that 79.30 is equal to the percent abundance of our first isotope. Well, we don't know what that is. I'll call that X, times the mass of our first isotope, 78.19 atomic mass units, plus the percent of our second isotope. I don't know what that is. I'll call that Y, times the mass of our second isotope. So now we have an equation with two variables. So we need to see if there is a relationship between those two variables, and of course there is. Our percents have to add up to 100%, so that means our decimal percents have to add up to 1. So X plus Y have to equal 1. So that means that Y has to equal 1 minus X. So now we can use that to substitute for Y to solve our equation. So that means that 79.30 equals 78.19X plus 1 minus X times 83.00. So 79.30 equals 78.19X plus 83.00 minus 83.00X. So now we collect our terms. So when we do that, 78.19 minus 83 equals, so we get negative 4.81X plus 83.00 is 79.30. All right, I'm going to bring the X over here and the 79.30 over here. So I get 4.81X equals 83 minus 79.3 equals 3.7. So X equals 3.7 divided by 4.81 equals, and let's see, I think I end up with, I don't know how many sig figs, so we'll just go with 70.769. So our first isotope would be 76.9% abundant, and then our second one would be 23.1%. So there we go. There's our answers. And I don't know if I did the sig figs right. Okay. Oh, next we're going to look at mass spectroscopy. Sometimes you're given the information in a graph. So here we have a graph, and we have our mass on the x-axis and the percent abundance on the y-axis. So for this particular element, we have 1, 2, 3, 4 different isotopes, and we can calculate the average atomic mass. So for the free response, we'll calculate it using numbers, and then we'll just look at qualitatively how we can figure out what the average atomic mass is. Of course, the average has to be in between 50 and 54, and it's going to be closer to 53 because that's where most of the atoms have their mass. So here for our average atomic mass, it equals, so our first isotope, 20% abundance, so 0.20, yeah, that's fine, times our mass, 50.0, plus our second isotope is also 20% abundance, times 52.0, plus our third isotope is 50% abundance, times 53.0, plus, and then our last isotope is 10% abundant, 0.10 times 54.0. So do that calculation out. 0.2 times 50 plus 0.2 times 52 plus 0.5 times 53 plus 0.1 times 54 equals. So we get an average atomic mass of 52.3 atomic mass units. So 52.3, so right there. And if we want to do this qualitatively, we could say that the 50 and 52 would average out to 51 at 40%, and then kind of do the same here. And so that's where our average atomic mass is. Okay, now we're going to move on to PES, or photoelectron spectroscopy. Now, photoelectron spectroscopy gives us information about our electron structure in the atom. And it gives us the idea of levels and sublevels. It is a validation of the quantum model of the atom. So it validates the quantum model of the atom. It gives us the idea of levels, main energy levels, sometimes called shells, and sublevels, or subshells. And from PES, we can figure out an electron configuration. When we are doing PES, usually the EMR is high energy. So we usually use high energy EMR, as in X-rays. X-rays have very short wavelength, very high frequency, and very high energy. So here we have a typical PES graph. And when we have these graphs, usually on our x-axis, which is binding energy, here the unit is joules, it could be electron volts, it could be megajoules per mole, but it's some kind of energy unit. And the energy is usually high going to low. So to do the electron configuration, we start with 1s2, go from the left to the right. So to figure out what element this is, our first peak are the innermost electrons, the 1s2. Then we have 2s2, 2p6, and 3s2. So if we look at here, this is giving us our relative height. So these are at a height of 2, this is at a height of 6. So our configuration, 1s2, 2s2, 2p6, 3s2, so this is magnesium. So the 1s electrons, the innermost electrons, held most tightly to the nucleus. This binding energy, you can think of that either as the energy that's holding the electrons in the atom or the energy required to remove the electron from the atom. So a common question is, if we had sodium, how would sodium's innermost electrons, where would they be on this graph? So this is the 1s2 for magnesium. What would sodium be? So magnesium has 12 protons in its nucleus. If we look at sodium, sodium is 1s2, 2s2, 2p6, 3s1, and sodium has 11 protons in its nucleus. So if we look at the innermost electrons for both sodium and magnesium, the higher nuclear charge exerts a greater force on the electrons, holding them in the nucleus more tightly. So sodium's 1s electrons would be to the right at a lower energy than magnesium. So I'll just draw that with a dotted line. So this is what sodium's 1s2 electrons would be. If we were looking at sodium's valence electron, so that would also be to the right of magnesium's, and it would be half as high. So maybe it would be like that. That would be sodium's 3s electron. Sometimes the question will give you the binding energy and will ask you to figure out the wavelength of a photon that would be needed to remove that particular electron. So we'll do a problem like that now. So let's say that this point right here is at 2.5 times 10 to the negative 18th joules. And we want to figure out what is the wavelength that would remove a 1s electron in magnesium. Okay, and I just made up that number. So to get the wavelength, we have the energy, and your AP equation sheet has those two important equations whenever we're dealing with EMR. So we know that E equals h nu and C equals lambda nu. So first we can find the energy and then calculate the frequency. Once we have the frequency, then we'll figure out our wavelength. So our energy is 2.5 times 10 to the negative 18th joules. H is Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. And that information that is on your AP equation sheet times the frequency. So our unit of joules cancels out, and our frequency, we'll calculate the number, and our units are 1 over seconds. Frequency is the number of cycles or waves per second. So 2.5 times 10 to the negative 18th divided by 6.626 times 10 to the negative 34th equals. So we get 3.8 times 10 to the 15th 1 over seconds. And now to get the wavelength, we're just going to use C equals lambda times nu. C 2.998 times 10 to the 8th meters per second. The speed of light equals our wavelength times the frequency that we just calculated, 3.8 times 10 to the 15th, 1 over seconds. The seconds cancel out. Our unit is in meters. Let me just calculate that. So 2.998 times 10 to the 8th divided by 3.8 times 10 to the 15th. And put that in scientific notation. And our wavelength is 7.9 times 10 to the negative 8th meters. All right, so up next we have UV-Vis spectroscopy. And UV-Vis spectroscopy is all about electronic transitions. Our EMR is going to come in. Our electrons are going to absorb that EMR, go to a higher energy level, and then of course they emit EMR when they go to a lower energy level. So our energy will be in the UV-Vis range that will excite electrons to higher energy levels. And we can use UV-Vis to determine concentration of a solution. Usually a solution that has a color. All right, so with UV-Vis spectroscopy, here's a schematic of what happens. So we have a light bulb. It's giving off all different wavelengths of light. It goes through a monochromator that isolates a particular wavelength. So only that wavelength comes out. Here is our sample in a cuvette. So I0 is our incident light. So it comes in, the solution absorbs some of that incident light, so less reaches the detector. And then our detector will give us our information in terms of percent transmittance, how much light goes through, or what we're going to be doing is absorbance. How much of that incident light our sample absorbed. How do we figure out what wavelength we need to use for our particular sample? So for that, we would run our sample under different wavelengths and measure the absorbance. So a graph of that might look like this, where we have absorbance on the y-axis and the wavelength that is being absorbed on the x, and we might have a graph that looks something like that. And if our wavelength is going, say, from 400 to 800 nanometers, so around 400 or 500 nanometers, our sample doesn't absorb, and then now here it is absorbing, and then when we get to 700-800, it's not absorbing again. So right here, this is our max absorbance, and then we would pick out the wavelength that would give us that max absorbance, and that's what we would set our monochromator to be. And we could pick anywhere kind of in this range where our sample is absorbing strongly. Okay, so for UV-Vis spectroscopy, our important law is Beer's law, or the Beer-Lambert law. Beer's law, Beer-Lambert law, which tells us that the absorbance equals A, B, C. The amount that the sample absorbs is directly proportional to A, which is the molar absorptivity. That is a constant. Absorptivity. That is a constant for our particular substance at a particular wavelength. B is the path length that the light travels through. So that is the width of the cuvette, and this is usually, and C is our concentration in molarity, and of course A, our absorbance. So let's take a look at the units in this equation. So A equals A, B, C. Absorbance is unitless. It's actually a logarithmic term, so it does not have units. So that means that all the units on the right are going to have to cancel out. So B, usually in centimeters, C in molarity, so that means that our constant has to be 1 over centimeters times molarity for the unit. And I do want to emphasize that this absorbance is for a specific wavelength. As the wavelength changes, the absorbance changes, as shown by this graph up here. So this constant will also be only good for a particular wavelength. Okay, so let's take a look at a UV-Vis problem. So here we have a 0.045 molar solution, has an absorbance at 535 nanometers of 0.62. What is the concentration of a solution that has an absorbance of 0.48 at 535 nanometers? So again, it'd be a good idea to pause the video, work this problem out on your own, and then come back. Okay, so the 535 nanometers, we're not going to need to use that, but it has to be that our absorbance must be taking at the same wavelength for us to be able to do any kind of calculations here. So we have, here is our, we'll call that our C1, our first concentration, and it has an absorbance, and we'll call that A1. We're looking for concentration C2 of our second sample, and this is our absorbance A2. And of course, they would have to be a solution of the same substance. If it was different substances, then you couldn't do it. All right, so we have our equation that A, the absorbance, equals A, B, C. So we can say that A2, our absorbance, our second absorbance, equals A times B times C2, our concentration. And we can put that over A1 and put this over A, B, C1. So our molar absorptivity, whatever it is, will cancel out. Our path length, whatever it is, will cancel out. So we're left with A2 over A1 is equal to C2 over C1. Absorbance and concentration are directly proportional. So our A2 is 0.48 and our A1 is 0.62. Our C2 is what we're looking for, and our C1 0.045. So just solve for C2, and that's molar. And we get 0.48 times 0.045 divided by 0.62 equals. Take that out of scientific notation, and we get 0.035 molar. Okay, so now we're going to look at a different type of problem. So Beer's law is very useful for figuring out the concentration of an unknown solution. And the way that it's done is usually we make a calibration plot. So whatever the solution is that we're looking at, maybe it's copper nitrate or something, we would take a stock solution of copper nitrate and then make dilutions and then plot the absorbance of each of those dilutions versus the concentration. So you get a plot, a series of lines, and what we want to do is draw the best fit straight line for our plot. So we're going to do the best we can. Hopefully I'll do this okay. All right, so there's our best fit straight line. So we can see that we have points that are below the line, points that are above the line, but our line is the best fit through those points. So our calibration plot is made with known concentrations. Now, if we have an unknown, we can measure the absorbance at whatever wavelength we are, and then use the concentration, the calibration plot, to figure out its concentration. So, such as an unknown solution, and that we mean unknown concentration, we have to know what the substance is, has an absorbance of 0.35, what is the concentration? Okay, so on our graph, our units on the x-axis are micromolar. Oftentimes, when we're doing Beer's law, we have these organic compounds that have very low concentrations that give you pretty good absorbances. So micromolar is 1 times 10 to the negative 6 times molar. So they're very dilute solutions. Okay, so our absorbance is 0.35, so we go on our graph to 0.35, go over to the line. You do not go to a point, you go to your best fit straight line, then go down, and then so there is our answer. So our concentration would be 3.3, 3 micromolar. So we get that right from the graph. All right, moving on, we're just going to briefly talk about IR spectroscopy. IR spectroscopy, so the EMR, the energy for IR is a lower energy than UV-Vis, and this energy causes bonds to stretch and bend, and we can use it for identification of bonds in a molecule, or sometimes identification of the molecule. So for IR spectroscopy, we have bond, bending, and stretching. And this is used for identification small molecules like alcohols or our bond type. We can tell if we have single, double, or triple carbon-carbon bonds. So the graph for an IR is usually goes from 0 to 100% transmittance. So 100% transmittance means that none of the incident light is being absorbed, and then here where the peaks go down, that is where more of the light is being absorbed. So this might be the bend for an OH group. That might tell us we have an alcohol. And that's really all I'm going to say about IR. If we get into organic chemistry, there's lots and lots of stuff for IR spectroscopy, but for us, that it's used for identification of molecules and bonds, and that it causes bond bending and bond stretching. And then for microwave spectroscopy, so that's a low energy form of EMR, and this causes rotation of molecules. So our example for that is for water. When you use your microwave, the microwaves hit the food, and it's the water in the food that is rotated because of the microwaves. So if we look at a molecule of water, we know that water is polar. We have a delta minus at the oxygen end and delta plus at the hydrogen end of the molecule. So we have a dipole pointing up from the positive to the negative. So the microwave flips the molecules. So we would go from this, our oxygen down here. So then our dipole flips that way, and then it would flip again. So as our water molecules are flipping, they're creating a friction, and that energy then is heating up the food. And that's all we're going to say about microwave spectroscopy. And then we're just going to finish up with a little bit of chromatography. Chromatography is used for separation of compounds in a mixture. And the separation is due to polarity differences. So there's many different types of chromatography, from very simple chromatography, like paper chromatography, to very sophisticated. I don't know how sophisticated, I don't know how to spell it. Sophisticated. Oh my God. Like high pressure liquid chromatography. But for every type of chromatography, we have a mobile phase and a stationary phase. And these phases will differ in their polarities, and our sample will be more attracted to one phase or the other. So we're just going to take a quick look at paper chromatography. Okay, so for paper chromatography, we could have a beaker, and we have, in the bottom, we have our mobile phase. And then we get a strip of chromatography paper. And then we put our samples, little tiny spots on our paper. So here, this will be sample A. We put sample B and maybe sample C. So A and B will say they're compounds, we know what they are, and C, we don't know what they are. So what we're going to do is put our paper, so this is our paper with our stationary phase, we're going to put this into our beaker. So when we do that, let me put our paper in. Our samples must be above the level of the mobile phase. So the paper is going to draw up the mobile phase, and these compounds are going to travel, and how far they travel depends on if they're more attracted to the mobile phase or more attracted to the stationary phase. So after they're in the beaker for a while, we may end up with a strip of paper that looks like this. So here is where A was, B, and C. So what this tells us that our unknown, if C is our unknown C contains compound B. It does not have A, and it has another compound in it, and we don't have information what that is. So unknown C contains B, no A, and some other compound. So this can be used to see if you have any impurities in a compound. All right, so that wraps up our brief instrumentation review, Unit 1.